Resiliency, design patterns in the cloud, and .NET. Just give a few people a chance to get in, get settled. A few more seconds. There's still definitely some activity. You're all a very wonderful audience. I can tell that already. You look wonderful, just from up here. Just to say that. Come on, come on, come on, come on. Come on. So I'm just going to start. So my name's Beeby. I am at the Beebs on Twitter. I work for Amazon Web Services. If you want to follow me on at the Beebs on Twitter, that would be lovely. Today I'm talking about resiliency and building resilient applications for the cloud in .NET. Fundamentally, we're going to be looking at, well, what is resiliency? Give you a little bit of an introduction to at least what I'm going to be defining resiliency as for the remainder of the talk. We'll look a little bit about infrastructure resiliency from a developer perspective, if you're involved in DevOps, thinking about what resiliency is and how to build resilient applications. We'll then look into the sort of more programmery .NET side of things with application resilience and how you build resilience into the applications that you're building. And then finally, we're going to be looking at resiliency engineering, or which is sometimes referred to as chaos engineering, and explain a little bit about what that is and how you might think about using it in the future. Now, the most important slide for me is the next one. If anyone's got a camera phone and access to Twitter, please have it ready, because this is my inception slide. This is me standing in front of a screen, standing in front of a screen, standing in front of a screen. It's 43 levels deep. This will be 44, level 44. My aim in life is to get to level 100. I've been a developer since I was 16 years old. I've been developing now as a professional developer for 20 years. I'll do the mathematics for you. That makes me 21 years old. I work at Amazon Web Services. I briefly worked at Oracle, and I worked for Microsoft for 8 years as a software engineer and an evangelist there. I've been building applications, and more recently, for the last sort of 5-6 years, building distributed cloud applications. And it's hard. It's really hard building distributed systems. And to show you sort of the complexity of some of these systems, this is Amazon's microservices self-discovered dependency diagram. So on the outside are all of the different microservices that Amazon use, and the interconnection between those different services, or the service dependencies. The sort of grouping, that arc, is the retail site, which spans lots of different things and has lots of interdependencies. The strong clustering is a signal that that particular part of the system is using lots of different dependencies. But it just shows you the complexity of a microservices architecture or a service-based architecture and how that works. So thinking about this from an architecture point of view, it can be really bewildering. And even if you're not building applications to the scale of Amazon, we're still building more and more complicated systems to try and create resiliency. Just to show you a little bit more about Amazon, specifically, Amazon, by the way, are AWS's biggest customer, probably, or one of the biggest customers. Netflix, another massive customer, maybe they're bigger, I don't know, in terms of their usage. But Amazon are a big customer, and just to show you sort of scale, on one single day, called Prime Day, which is like our big sales event at Amazon, there's more details if you're interested to know the infrastructure for that, how we support a Prime Day selling day. But just to give you some statistics, 7.11 trillion calls to our DynamoDB service, which is our NoSQL backend, peaking at 45.4 million requests per second. Mostly my IIS web server wouldn't handle that generally, and then we have we don't have an instances metric. We have a thing called server equivalence. But basically, the start of Prime Day, we had 372,000 server instances. And to manage the load of Prime Day, we scaled up to 426,000 instances. 426,000 instances. So it's a big infrastructure project, something like Amazon or AWS. And when you're building something like that, you can guarantee that failures are a given, and everything is going to fail. So here we have failures are a given, and everything will eventually fail over time. If you ask the question, is Amazon.com broken? The answer is yes. Right now, something in Amazon.com is broken. But whether or not you would notice is a different story. I mean, think about using Amazon. How many times is it broken, unresponsive, unable to add information to the cart? Very rarely. And that's because it's a very highly resilient application. And one of the things that they do is there's patterns for building reliable, resilient infrastructure. And one of the things is, as a software developer, to build reliant applications. And I'm going to be talking about some of the patterns that we use at Amazon and AWS to build services that scale to the sorts of levels that we've talked about. And I'm going to do it from a .NET lens. So resiliency, this is a quote from me just now, is resiliency is the ability for a system to handle and eventually recover from unexpected conditions. So it isn't meaning that your application's always online. It means that even despite really complicated scenario situations, somehow you're still able to solve your business function. You're able to continue doing what you're doing, delivering things to customers, taking requests, somehow, some way, changing a wheel randomly as you're driving along. A very resilient driver, this driver. Doesn't stop for anything. And really, that's what we were trying to build. We're not trying to build applications which don't fail. We're trying to embrace that failure and build applications that do good things when failure happens. They can handle failure. They can handle difficult scenarios. And if we look at the infrastructure piece first, one of the simple things to do is to improve availability of your applications. So you may have seen 9 nines, 3 nines, 4 nines, 6 nines, 9 nines of availability. Really, availability numbers, if you are able to build one system which has an availability of 99 or 2 nines of availability, that means that its downtime every month is 3 days and 15 hours. Simply by taking that 9-9 available system and duplicating it and placing some kind of load balancer which is fault tolerant in the middle, you'll be able to increase the availability of that system by 2 nines, so it'll be 99.99, just by adding another copy, effectively. As long as that copy sits on a completely different system, which is different network, different power, a completely different system, you would basically enable yourself to get more availability. 99.99, 4 nines of availability is 52 minutes of downtime a month. Sorry, a year. And then we have, if we take the same application and we replicate it 3 times, then we get 6 nines, 99.99999, roughly availability. So at AWS, when we give you service level agreements, what we mean is that we've architected applications which have got availability like this. And the reason we're able to do this is because of the way that we structure our data centers. It's really important as a part of an infrastructure thing that you understand how AWS solves these sorts of problems, because it's a very complicated problem to solve. And it's important I just sort of explain to you a little bit about how the infrastructure AWS works. And this is similar for other cloud providers, but not the same. This is our closest region here in Romania, Frankfurt. And you'll see that it's a region with 3 availability zones. And those availability zones contain multiple data centers. A lot of people, when we say we have a region in Frankfurt, assume that we have a single data center in Frankfurt. We have many, many, many data centers in Frankfurt. We have 3 availability zones. Each of those availability zones is made up of many data centers. Each of those availability zones have separate power and separate networking, separate systems. They're completely isolated units. I think we are still the only cloud provider which also, our availability zones are not in the same building. They're not just thick walls or slightly separated buildings separated by a few meters. Each availability zone is separated by a good distance, a number of miles. A distance big enough that the latency doesn't become a problem between the different availability zones, but short enough so that the latency isn't a problem, but far enough away that if lightning were to strike or a regional natural disaster were to strike, our availability zones would stay available. We don't do what some providers might do, which is just have a building with separated sections and call that an availability zone. These are separate buildings with some distance between them. And it's important because if we're talking about like redundancy of availability, if lightning strikes, you still want some of your availability zones to be available. So if we're building a region in a place, AWS will build a region. We have a number of them around the world. We will then create 3 availability zones or more. Some of our regions have more than 3 availability zones, but they have a minimum of 3 availability zones. They have high-speed private fiber links between each data center. And the idea is, if you're an application developer, is that you want to be building applications which span these availability zones, so that if one were to fail, then the others would take over. So let's just say we had a simple application with a number of instances. At AWS, we call virtual machines instances. Just in case you don't know what I'm talking about when I say the word instance, lots of people don't. Say instances, and I put some instances in each availability zone, and I put a database instance, which I'm managing myself in this instance, in a couple of in different availability zones as well. Now, a big major outage happens at AWS, and an availability zone goes down. It happens. Failure always happens. What happens to your application? If your application just sat in availability zone 1, then your application would be offline. But if you've had an elastic load balancer, it would basically route your traffic to the other availability zones, and then your application would remain online. So your users wouldn't know that anything's kind of gone wrong. Now, you might look at the elastic load balancer and think, well, that's a single point of failure, isn't it? But the thing to remember is that every AWS service that we develop is architected across the availability zones, so that we also can withstand failure in one or more availability zones in this region. So the elastic load balancer actually isn't a box which sits on one of the availability zones. It's something we've architected, and that's true of all of our services. So if you want a Microsoft SQL Server, then we have a way of sort of spanning that across the availability zones. So the way we build services is this. We span them across availability zones to have high availability. If you want high availability in your applications, what you have to do is create multi-availability zone architecture or multi-AZ architecture. It creates sort of fault-tolerant applications. All of the AWS regional services use this sort of process. And anything like S3, which are storage, or load balancers, they're all using this sort of pattern to work. So one of our services is called Elastic Beanstalk. It's the easiest way to get a .NET application running in AWS if you just want to run it on IIS. Let's forget about containers for a second, and we'll just say we want to take a website, and we want to get it working on AWS. So you would go to Visual Studio, create a new web project, create a regular .NET 3.5, .NET 2 application if I wanted to, but I'm going to do an ASP.NET Core application. Call it .NET Days Row. Create it. And what will happen is this is currently just nothing AWS here at the moment at all. We're just creating a regular application. We create that. That will just build as a sort of boilerplate ASP.NET Core web application. And then what I want to do is go and take that and run it on this Elastic Beanstalk service. And I'm going to try and create a multi-AZ architecture as well when doing this. I don't want to give feedback to Visual Studio. So I'm going to right-click the project. And where you'd also ordinarily have a publish to another cloud provider, because I've got the AWS SDK on there, it says I can publish it to Elastic Beanstalk. And I say I want to publish it to EU Frankfurt, and I want to create some infrastructure to run this project on. And it's going to ask me some questions about, like, what's my system. So I'm going to just say I want to create one environment. I could have multiple environments, but I'm going to create a product environment because I'm a maverick. I'm going to choose the container type or the instance type that I'm going to run. So this is Windows Server 2016 running IIS 10. I'm going to choose the instance type. I want to say that I don't want a single instance environment. I want a load balanced environment. I could choose to enable rolling deployments to do blue-green canary deployments, but I'm not going to do any of that. I'm just going to literally choose my instance type, and choose next. It will then set some roles, which I'm not going to go into how security works in AWS. That's another 45-minute talk. But I'm just going to put into release mode my .NET application, click next, and then on the final thing, it will give me a review, and I can just say I want to deploy that application. So it builds the .NET application. The AWS SDK is then going to go and take the AWS toolkit for Visual Studio is going to take the application, do all the building stuff that you would ordinarily do in command line, I guess, or you'd do it in other ways. It takes your package, uploads it to Elastic Beanstalk, and then when I'm inside Visual Studio, once that's done, I can go to View, AWS Explorer, and I can explore my AWS stuff from within Visual Studio. And I can go to that, I can click on the Beanstalk environment, and it gives me a URL. I could then go and attach HTTPS certificates, my own custom domains, those sorts of things to it, but it's fine as it is, it works. What's actually happened is Elastic Beanstalk has created a number of instances for me. It's created me a load balancer, and it's created me an auto-scaling group. Now, auto-scaling groups are important for this, and I'm just going to show you. You can see all the parts that make this up. This is an auto-scaling group in AWS. And what this is saying is that I've got a group of servers, and I've got currently in my infrastructure, I've got one instance which is running. I've got a desire for creating one instance, a minimum of one instance, and a maximum of 4 instances. If I were to hit this URL with loads of traffic right now, based upon my scaling policy, it would scale up or down depending on, say, you could say, if there's this much network traffic, then start scaling up or down, right? So it's pretty simple auto-scaling stuff which is happening. Now, because this particular auto-scaling group has access to multiple availability zones, and you can see the availability zones it has access to here. I've got A, B, and C in that region. When it creates new instances, like for example, if I go into that auto-scaling policy, I say, I want a desired capacity of 2 currently. It will add 2 instances to the infrastructure. So I change the desired capacity to 2. I'm not actually changing minimum capacity. So eventually, this will scale back down to 1. But I'm just changing it for a temporary period of time to 2 manually. It will create a new instance, and you'll notice that the second instance is placed in availability zone B, and the first instance is in availability zone A. So now I have those 2 instances which are load balanced in 2 different regions. I've basically got 99.99 availability on that application. If I want to add another instance, if I said scale up to 3, it would put it into a third availability zone. So now my application is spread across 3 availability zones, 2 availability, however many availability zones you want, or however many available in that region. And the more availability, the more failover you'd have. So now, auto-scaling is interesting, though, because I created 2 instances, and it placed one in one availability zone and one in the other. But one of the cool things about auto-scaling in AWS is that we can say, as long as it's 1 or over, I'm saying to AWS, I always want 1 instance. So if I had 1 single instance in availability zone 1, the auto-scaling group, if availability zone 1 sort of failed, the auto-scaling group would say, well, I need 1 instance. I've promised, the auto-scaling policy has promised 1 instance. So it will then create a second instance in availability zone 2. So there'll be some downtime, but eventually, in a few minutes, the new instance will be created in zone 2. And then all the traffic will then be linked over to availability zone 2. So you don't actually have to have 2 instances running in parallel to have the ability to switch between availability zones. Now, that's really good for stateless applications, where you've got applications which don't have state or memory or something involved in it. And it becomes a little bit more complicated if you're wanting to manage state or connection. So Thomas, in the last session, was talking about real-time applications, and some of that stuff requires maybe in-memory caches and things like that. He mentioned the concept of a backplane in real-time applications. What I would recommend if I was building if it was in AWS, I would go and find the service for Redis. In AWS's instance, that's called Amazon Elastic Cache. And realize that AWS has spent a lot of money developing a distributed Redis infrastructure for you. You don't have to manage it. It's AZ fault tolerant. And so you would basically store information about the messages going into something like Elasticache, maybe using their subpub, or maybe just caching it directly to Redis. But you could probably start thinking about, well, how do I start stop relying on the state of the actual box that I'm using and start using services which are outside, or build services which are fault tolerant and highly available using the availability zones. So it becomes a little bit more complicated creating auto-scaling groups when you're dealing with stateful applications, but it's completely possible. Now, I showed you how to create an application kind of in Visual Studio, but there's also another way in .NET to do it using .NET to create infrastructure, and it's my preferred way. It's the way I build infrastructure. So if we want to create the same resilient infrastructure, we might use something called the AWS Cloud Development Kit. It's got a really beautiful video on the front there. Great guy speaking, explaining what the Cloud Development Kit is there. I recommend you watch that. It talks about like what this Cloud Development Kit is. And basically, it allows you to take the language of choice, whether that be .NET, Java, PowerShell, or whatnot. There's a couple others. Go, I think, is coming. There's a few languages, but .NET's the obvious choice for me. And then you can create infrastructure in .NET and then build it and deploy it. So to show you an example of that, here's the .NET a CDK application. And on the first instance there, on line number 14, I said I want to create a new virtual private cloud, which in AWS terminology is like basically your network, your private network. It's how you secure your own network. And I want it to span a multiple of 3 availability zones, or use a maximum of 3 availability zones. So this is going to create a network for you which is able to access all 3 availability zones. And then I'm going to create a container cluster by just using this line. I say I want a cluster inside that VPC, and I'm doing it all in .NET. And then I create a task definition. We're using, when I said a cluster there, this is our container service. So you could do this on Kubernetes. We have similar code to write a Kubernetes cluster, but this is a cluster called ECS, Elastic Container Service. And I'm creating a definition here called a Fargate task definition, which is basically a description of the containers that I want to run. And the important line here is like line 28 to line 30-ish, where it's basically saying, I don't currently have a Docker image, but I've got an application on my machine, which is a Docker image. Go and build that. So you'll see there's a .NET app folder. It's a standard .NET application. In the root of it, it's got a Docker file. And what the CDK will do at that point is it will, when it's built your VPC and it's built your cluster, it will then go and build your Docker image. It will put it into ECR, which is our container registry, and then it will go and deploy that to however many places you want to put it. I map some ports, container port 80 to host port 80. I add that port mapping to my container definition, and then finally I say what my container specification is. I want containers with a memory limit of 512. I want a maximum 256 CPU, and I want 6 of them. 6 desired count equals 6. I want 6 of these containers running for me, please. And then I say create an application load balanced Fargate service, and we have these, we call them constructs for every service in AWS. If you want to create an S3 bucket, you could do it like this as well. And what I can then do is go to a command line. I type, oops, sorry. I go to command line, I type CDK deploy. It executes the application, and it deploys that application to AWS. And if I were to deploy it once, and then call CDK deploy again, it would only change whatever's changed in my code. So if I added an S3 bucket, it would add an S3 bucket. If I changed the desired count to 4, it would change the numbers of containers that I wanted. What it will eventually do is build my Docker image, upload it, output a load balancer for my containers, and then I can click on that URL, and it's got my containerized .NET application over 6 containers, span across 3 availability zones. If an availability zone went over, the 6 containers would be created in the other availability zones, but I'd already have containers there which are hot. So users would never know if an availability zone failed, and my website would be highly available. So there's 2 methods there to create highly available infrastructure. It's specific to AWS, what I've shown you here, and some of the availability zone infrastructure is specific to AWS, but there are similar concepts in Azure, and you would do similar things if that's your preferred cloud. I don't want it to be, by the way. Like, come and speak to me if you want to change your preferred cloud. But it's interesting. These are interesting ways we can start building infrastructure as code with .NET in AWS. So let's talk a little bit about application resiliency. So I've talked about infrastructure. So we've got highly available services which are fault-tolerant and resistant. They're Dockerized, containerized applications with highly available load balancers. That's great. But what happens if your application isn't good? What can you do to protect it and make it more resilient? The problem with applications isn't that they're generally badly designed. It's that small problems generally lead to big outages. So little things, just a little tiny problem, a little timeout problem here, a little latency there, all of a sudden has an impact which creates a bigger, more large-scale, cascading problem. I'm just going to leave this to play out because there's one more beautiful thing in this video. And it's just this sort of moment when he gets that, right, I'll fix this. No, that's broke. Someone page operations. It's little things in your applications that actually cause cascading failures. And we'll talk a little bit about that with a simple example of a user connecting to a back-end service which then calls a database. If the database were to slow down, what happens with these connections? So it really all depends. If you were looking at this infrastructure and say, what will happen if the database starts slowing down? You would probably need to know what the timeouts were for both sides. The client timeouts in JavaScript, the client timeouts for the client on the back-end service, and maybe the client timeouts for the timeouts for the database as well. Does anyone know the timeouts for, well, let's just have a quick look. So if we've got a request coming in and we have an insert request going in, and the database starts slowing down, what does the client usually do? Well, it probably starts to retry. Now, we've got a connection open to that database, okay? Not a problem at the moment. But most database products have infinite timeouts or very long-lived timeouts. And if you don't set them, then that connection will remain open in the connection pool for a period of time. But the client side has got 10 seconds of timeout. So what it does is goes, well, it failed. I'm going to retry. So it makes a retry. It makes another request to the database. The database is struggling for some reason, whatever that is. It's trying to do an insert. Well, that's timing out as well. Well, then the user goes, well, I want to go and try again. So it does another retry. We've got an insert. It fails. And before you know it, you can't get a connection from the pool. You have like a cascading failure, effectively. You've distributed denial of service on your own servers, right? This is a problem which there's many ways of defending against and creating stuff which solves this problem. So just with a show of hands, does anyone, without looking at documentation, know what the default timeout for HTTP client is? 30 seconds. Any? 100 or 30. So hands up who thinks it's 100. 2 or 3. And hands up who thinks it's 30 seconds. Look, everyone thinks HTTP client is 30 seconds. This shows the sort of problem because actually it's 100 seconds. And well done, those two people. I will buy you a drink later. And it just goes to show that we don't think about the timeouts between connections generally. We should, and we should start thinking about them more if we want to build resilient applications. Simple way is to set a timeout on your HTTP client. Now, if you've got that was basically just saying I want to try a time span timeout for 5 seconds on my HTTP client. That's probably too low, but basically, if it doesn't respond within 5 seconds, then the connection will be disconnected. And a similar thing would be done with your database connections, entity framework timeouts, all the things that may be connections, which you should know what the connectives of your service dependencies, what the timeouts of those things are, and what the SLAs are, and what you should be doing if those things fail, because they will fail. And I think we're far too used to, I was at least, building smaller systems on 1 or 2 servers and solving the problems as they came along, but not really thinking about what the problems might be. You can get away with that on a system which is quite small. But as soon as you scale that system up, as soon as it becomes bigger, there's more and more dependencies, those failures become uncovered, and they get uncovered in production. So if we were saying, OK, I've got this simple ASP.NET controller, and at the moment it's basically making a request over to a URL, and it's not covered in any way. I've not got any exception handling or anything on this at the moment. It's just out and out saying 5 seconds. There's a 5 second setup on the HTTP client. I'm using a new C#. What's that called? Using parameter. It's not using in the right way in the way that it used to, but it's using the new C# 8 just because I was fancy pants, and JetBrains told me that I could do it, so I tried. So the new using declaration. So I basically created this new HTTP client, which will dispose automatically at the end after it's finished. I've said, I call the API, I take the response, and I JSON serialize it and take that back. Now, this particular application, this API at the moment, responds really, really fast. So localhost 500 API weather forecast. If I call this API, it responds really fast. The timeout's set at 5 seconds. There's going to be no problems here. It's going to work. So if I click up on the up here and click fetch data, this is the standard .NET ASP.NET Core template. I think it's a React template. If I click fetch template, it's going to call the API in the background. I'm going to get some weather data. It's actually randomized weather data, which I get back. It's not real. Because it's definitely not -10. So that's fine, but then what if I call the API? I've sort of created an API here on the end, which is, if I add the word delay to it, it adds a delay, a random delay to the timeout, which is probably going to be more than 5 seconds. So now, basically, I'm sort of creating an environment where my API is responding in 10 seconds. So it's below the SLA that I had for this particular URL. So I've got a HTTP client, which is going to time out after 5 seconds, and I've got a URL, which is probably going to take longer than that to respond. So well, what will happen? Well, in my React application, I get this. When I click fetch data, I get loading, because I'm not handling this scenario really at all. React's doing something. It's not actually showing the error. But what it's doing in the background, there's an error. There's some debug errors in there. Ignore the socket exception. This is a timeout error, but the debugger is telling me about the sockets not being able to connect as well. So we've got some kind of error from our controller because basically it's timed out and I'm not handling that exception in any way. Now I could wrap that in a try-catch. I could do some stuff to handle that resiliency, but there are libraries which can help us, and one of those libraries is called Poly. Poly.NET. It's a resiliency library built by the community. It's open source, and you can go use this and start building with it today. Lots of people use it in production in .NET systems. I've seen lots of my customers use Poly in production. And what it does is you install it via NuGet. You add the reference Poly to the top of your application. Now, I'm going to show you how you would do it like at an individual level, but there's also some system-wide settings that you can set to like every HTTP client to apply a policy to, but we're going to do it to a specific controller at the moment. So I'm going to say, I'm going to create a new policy. It's going to be called a timeout policy. And this timeout policy is going to say, after 10 seconds, timeout. And basically, a policy will wrap some execution. It will wrap a function or some C# calls. And it's basically going to say, if this piece of code takes longer than 10 seconds, then I'm going to time out. And the way it times out is it passes in a cancellation token, which should cancel all of the different things that you've set it up for. So I've created a policy called a timeout async, and I set it for 10 seconds. Anything I wrap in that policy will only be tolerant of a 10-second timeout, and then it will stop. I've also added a fallback, which says, I'm going to catch an error called timeout rejected exception. You can see it over here, timeout rejected exception. And if that exception is thrown by whatever code this policy wraps, then I'm going to fall back and provide this information. Now, this is just me hard coding some information into my service, but this could be retrieved from cache. It could be retrieved from a separate secondary service. There's lots of different things where this information could come, but I can't get it from the weather API, so I'm going to get it from somewhere else. In this instance, I'm hard coding it into the service. It's very resilient, but not recommended. And you can see that it's coming from this because it sets the temperature to 0, and it says this comes from a fallback. So we can see visually that it's coming from the fallback rather than coming from the API. What I then do is I sort of connect these policies together, and I say, I've got a fallback for timeout, and I'm going to wrap the original timeout policy that I created. So I've got this sort of chain. So anything which executes inside of the policy and it throws this timeout exception is going to get handled by this particular fallback. And I'm accepting timeout rejected exception, but I could handle any exceptions with this fallback, depending on your system and what it's capable of doing. So I'm going to then have this piece of code, which is basically wrapping. It's got that policy .wrap, and it executes async some functionality. Now this, at the moment, is just my HTTP request, which it's wrapping. So HTTP client, I've actually removed the timeout because I'm going to be relying on the timeout now from Poly, but you could still have one if you wanted. And I'm going to call the delay API. Now, this is going to fail because it takes longer than 10 seconds for this delay API to return. So one thing I've changed about it as well is that I've passed in a cancellation token to the request. And you'll see that execute async on this policy wrap has a thing called a cancellation token, which basically the timeout policy is going to pass into this function. So that if it times out, it's going to pass the cancellation token to this particular response, but it could pass it to any asynchronous request in .NET. So it's basically going to time out anything inside of there. It's going to call this timeout. If I didn't pass the cancellation token or use it properly, Poly would still time out this, but I would still have those threads open, potentially, because they're not cancelled. So this is explicitly closing or cancelling any asynchronous work. And now, if I call that API, the API delays, so I get this response, and I've got a fallback now, which is not great, but at least it's not crashing or saying it's loading anymore. It's giving me something. And if I go to the controller and just execute that and look at the JSON response coming back, you can see there's the JSON response. That comes from the hard-coded JSON response that I set up as in my fallback. So how else could we have fixed this, right? Yeah, the servers are failing in a retry situation, but how else could we have potentially fixed this? Now, at the moment, I just execute that once. I don't retry it. I just call it once. But if we did a retry, how could we do that in Poly? Well, we'd add another policy called a retry policy, and I'd say, create a new policy, this policy is going to handle any exception. So any exception which the code throws, it's going to still retry it. I probably want to be less broad with my exception handling there. Probably want to capture specific scenarios. But I say, if I capture any exception, I'm going to try it again, and I'm going to retry it 5 times. So you'll see the retry count is 5 times. So this is going to execute that HTTP request 5 times, immediately one after another, and see if it gets a better response. And if it's an intermittent issue with the back-end service, this would solve that problem. And now I've got a general fallback, which falls back and says, if after 5 retries, effectively, I want to call this fallback, which says this comes from a fallback. So the way that I connect this together now is I have my fallback, which I'm wrapping in a retry policy, and I'm wrapping the timeout policy. So it's going to call it 5 times. And what you can see is you could create these policies separately and sort of make them work in different ways by using these policy wraps. So now I've got the same piece of code, but now it's going to retry 5 times. Now this is that problem which we talked about, which was executing it straight away. If you've got a connection pool which is 10 seconds, let's say, or 100 seconds, your retries are just going to keep smashing the service, and we're going to get into the same problem. Now, if we change the timeouts for our database calls so that it backed off after it stopped, it timed out after 10 seconds, and then we use something called a wait between our retries, an exponential wait, the first request would happen instantly, but if it failed, the second request would happen, it would wait 2 seconds, then try again. Then it would wait 4 seconds and try again, 8 seconds and try again, 16 seconds, try again, until it got to the retry limit. So it would retry, 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 retry. And what that would mean is that we wouldn't get in this instance with the database, we wouldn't get the DB connection pools failing because the timeouts would have a chance to recover from it. Or we potentially have slowed the system down a little bit to back off and stop doing creating some of that problem. Now this is good because the connections are released. But we can do a little bit better than just an exponential back-off. And this is how we would add an exponential back-off. It's a similar retry policy, but now I use this little thing saying wait and retry. Retry 5 times, and then I say the retry should happen, we should wait, based upon a time span from seconds of the number of retimes to the power of 2. So the retry attempt is going to be passed in by Polly. So it's on the 5th time. So the 5th retry attempt to the power of 2 is how many seconds it's going to wait before it retries and executes. So now we have retries happening. But now we have a problem that if we have a failure on our database, all of our current connected clients, they're all doing exponential backoffs. What happens is connections start pooling at specific times on 2, 4, 6, and 8 seconds, because the connection failures happen usually time-based. And if you have a distributed system, what happens is your connections now start clustering based on the exponential backoffs. And you actually can start overloading your system because all the clients are retrying after 2 seconds, after 4 seconds. And there's a correlation in a distributed system, which means that you get this sort of graph with the requests. So to change that, instead of doing it arbitrarily 2, 4, 6, and 8 seconds, we add a thing called a jitter, which is just a random number which we add to the back-off time, which means that all the different clients will be using slightly different exponential numbers to retry the connections. And so to add a jitter to that retry policy, we basically add this line on line 35, which says add to the exponential back-off time, add a jitter number between 0 and 1,000 milliseconds. So now instead of 2, we're going to have 2.5, 2.6, 2.7, and it just smooths out the request patterns from all of our clients in a distributed system. Well, that's great. We've got 2 services in 2 different availability zones, and they're getting lots of request handling it, and there's not really a problem. And then all of a sudden, we get a peak load. And we stop being able to handle it in the same way. And we start getting failure. And it's just the case that these 2 systems are overwhelmed. Now, you could solve this by adding more people to that chocolate, conveyor belt. We also could just slow down the conveyor belt, stop the requests coming into the system. And to do that, there's a pattern called the circuit breaker pattern. And Polly is a really good way of doing this circuit breaker pattern. Basically, it's wrapping a protected function, and it's monitoring it for failure. And if a failure happens over a certain threshold, then it's going to actually stop making requests. So again, I have to rejig slightly my application. Before I was doing it all inside of a controller, and the problem with that is that all my policies were stateless. They were being recreated on every controller creation. So I need to actually make a singleton, which is going to store all of my policies. So to do that, I've created this thing called a weather client. It's just a C# object, and this is where my logic, my retray logic, is going to exist now. I'm using .NET Core, so they've got a dependency injection library. I'm going to add this as a singleton and say add the weather client as a singleton object, and then I can go into my controller, and if I say that I want a weather client and I didn't pass it in, the dependency injection controller is now going to pass the weather client in for me. And because I've added it as a singleton, I can guarantee that this weather client will be the same across all connections. It will be shared across all controller connections. And that's important because of this circuit breaker policy, which I'm saying it's just another policy I add in my wrap, and I say allow 7 exceptions before breaking, and then once you've had 7 exceptions, wait for a minute before you retry. So I can still have this exponential jitter, but I can say if it fails 7 times, stop calling this service because it's not going to work. Wait a minute, and then try again. And what the circuit breaker will do is it will let 1 request come in after 7 failures. It will wait 1 minute. It will then let 1 request come into that function. It will test it. If it fails again, it will break the circuit for another minute. And there's lots of complexions you can create with these circuit breakers, but this is a simple one saying, if it fails 7 times, wait for a minute. I've also added a specific failback for the circuit breaker. So if the broken circuit exception is thrown, so a circuit's failed, then I'll fail with this, saying that the failback was because of the circuit breaker rather than just a general exception. So you can handle all the different failures with different fallbacks, and you can have multiple fallbacks. And you end up with a wrap. Now I've got a resiliency policy for making HTTP requests. It's going to do a circuit breaker fallback, a retry policy, a timeout policy, and I've just noticed I've made a mistake there, because you'll see I've put it in twice, but never mind. Let's ignore that. And what you will end up now with is a resiliency pattern for calling APIs, where it will time out, it will be able to retry, it will jitter, it will do all the sort of best practices in quite a sensible, easy way. So I highly recommend looking at Poly if you're a .NET developer and you want to build more resilient applications. And finally, I've run out of time a little bit, but I just want to touch on this. AWS and Amazon, we practice this concept called resiliency or chaos engineering. Another big practitioner is Netflix. Netflix, one of the pioneers in this kind of engineering principle. And Amazon have been doing it since about 2008. And it's based upon this idea of fire drills. Before you become a firefighter, an active duty firefighter, you need to spend approximately 600 hours in training to be a firefighter. And after that, most of your time as a firefighter isn't actually fighting a fire. It's training and learning how to fight fires. Now, if you think about your own careers, how much time do you train dealing with issues and production issues and resiliency issues? How much training do you do on that subject? How much experimentation? How many times do you test to see if your systems, what happens if this particular part of the system fails, and actually try it? Probably relatively little. You probably don't do that very much. Most people don't. And what chaos engineering is about is like making that part of the way we develop software. We have these things, which is, we have these times when we will practice failure in our system. Netflix will, every month, whilst you're using Netflix, every month, they will completely shut down, arbitrarily, one of their regions, for example. And they'll carry on working. In production, they do this. You probably won't have noticed that happen. And the reason you don't notice it is because it's resilient. And the reason they do it in production and not on some test environment is because they want to see what real traffic, what happens in the real scenario when they have a full region failure. And so they're very highly resilient because they do this so regularly, they become aware of it, and then they're not having these like 3 a.m. calls where their applications are down because they've already tried and figured out what problems might occur. They hypothesized about the problem, they created an experiment, they ran a real experiment in production, and then they explored how they could mitigate it and build more resilient applications. There's a guy called Jesse Robbins, or he was at Amazon, he recently left. But he kind of brought this concept to Amazon in around 2009, 2008. And the reason is because he was actually an ex-firefighter. And he looked at the way that we built operations and built services and said, we should practice more about failure if we want to build more resistance to systems. He's called the master of disaster at Amazon. And he will literally go around and unplug things. He does it a little bit more organized in that, but literally will destroy systems intentionally to see what happens. It sounds fun. He created this concept called game days, where basically they have a game day. There's a known period of time in the day when we're going to have a failure which we're going to cause, but all our engineers don't know how it's going to be caused or what's going to be done, and they're going to switch something off. They're going to destroy something. They're going to inject code into our live running applications and see what happens. It's kind of irresponsible, but it's also really, and I'm not suggesting do this tomorrow in your production systems. You need a lot of planning. Look at some chaos engineering work to figure out how you do this. But the best practitioners are doing it in production. But you might do this in sort of a staging or dev environment. I'd definitely recommend that to start with. But it's good at exposing the kind of architectural problems that I've talked about already. But it's really good at exposing what we call latent defects. And these are problems that appear only because of failure you've triggered. For example, we discovered not problems with our systems at AWS and Amazon, which were related even to the applications that you wrote, but because of an outage, we found that some of the software which we used to manage the outage couldn't handle the concurrency, and so we weren't able to solve the problem. So there's problems with our application, there's problems with the way that we communicate, and you only really discover these problems if you actually practice what would really happen in a real scenario. So if you want to look up at Jesse Robbins and that information, I'll send some links at the end which explains a little bit more about that. We also have the ability to inject inside of, not just switching off instances or crashing regions, but also inject problems into our live running applications. And my favorite attack, by the way, in Chaos Engine is called the Paul attack. Does anyone have someone in their office, we call them Paul here, but someone which just knows how everything in the system works and how good, if you've got a problem, you go to Paul and you say, hey, Paul, how do you fix this? And he fixes it. Yeah, a Paul attack is saying, Paul, go home, then causing an outage. And then seeing how everyone else copes with the problem, and Paul's not available. And that's these failure injections. We have a number of different libraries. This particular one, Simmy Army, is one which is developed by Netflix, and the one that they use for their injections. There's a .NET library called Simmy. It's written by the same people which write Poly, and you can inject in the code failure, which you could switch on and off. Like, you don't want it running constantly. So we can inject a chaos policy, for example, into that HTTP client request. We could say, inject some latency of 5 seconds, and I'm going to enable this policy. And I can make that part of my HTTP client request, and then have a dashboard somewhere in operations which switches this particular failure on. And then all of a sudden, all of my HTTP requests across my entire estate, or a proportion of them, will have this enabled, maybe through an environmental switch on some machines. And how do we then start dealing with that? What happens to our application? What systems fail and fall over? It's something to look at, but it's the point I'm trying to make, I think, with chaos engineering generally, is that quality in softwares is not an act, but it's a habit. And that was from Aristotle, from somewhere around 350 BC. Quality is an act, not a habit. You have to get resiliency as a habit of your whole engineering team. It's a people problem more than a technical one, to think about these sorts of issues. If you want to dig deeper, there's a few blogs that I'd recommend from my colleague Adrian Hornsby. It basically talks about all the things that I talked about, but it goes much more deeply. And there's a few people taking pictures of this. If you just follow me on Twitter, I'll send all these links after, including the slides and all the talk code as well, which I had. So we looked at resiliency today, infrastructure resiliency, application resiliency, and lastly, resiliency engineering. My name's Martin Beeby. I'm available, these are my contact details. If you scan that QR code, by the way, you will get you can rate this talk and get a $50 AWS credit for the first 40 people which rate my talk. Please give me feedback there. Tell me how the talk went. If you hated the talk, give it 5 stars. If you loved the talk, 5 stars. Also, there's some contact details there. Please, if you found anything interesting in this talk, please do tweet about it, because that's what gets me to speak at other conferences. So please say, oh, Martin was a good speaker, or I enjoyed that thing. It also helps me become a better speaker. If you loved it, if you thought I was great, please tweet at the Beebs on Twitter. If you hate this talk, if you think I'm an idiot, if I've wasted your whole hour in the last 45 minutes, please email me at mbb@amazon.com. Thank you very much indeed. Now, I don't know if we're kind of running out of time. I know we're into lunch. I just need to take a picture for my mum. We've got a whole hour, so if you've got questions, I think maybe it's possible to come and speak to me in lunch, because if I explain how AWS handles DDoS attacks, then we are in trouble. I could be here for a long period of time. So come and ask me at lunch, and we'll speak about resiliency. Thank you very much again.